Hey guys, we're going to go ahead and get started with Chemical Reactions podcast number 7, which is an introduction to redox reactions. So up until this point, you've been learning about how to categorize reactions based on how species behave and interact with one another to form products. All right, so we've learned all about these different types of reactions. Well, in this podcast, I'm going to introduce you to a whole new way of classifying and identifying chemical reactions. And it's based on electron transference from one atom to another during a chemical reaction. Couple definitions here. Metathesis reactions. These are reactions that do not involve any transference or movement of electrons from one species to another. Examples of these would be all double replacement reactions, including neutralization reactions. And of course, we also talked about the evolution of gas with species that spontaneously decomposed, like carbonic acid. So after we've gone through the next several podcasts, I'm going to have you guys kind of go back and look at some of this and put it all together. But metathesis is a fancy term for reactions that do not involve transference. Now, our new term is an oxidation-reduction reactions. And in chemistry, we're going to refer to those as redox reactions. And these are reactions that do involve electron transference among species. We're going to look at a couple examples here. I want to look at iron 2, and so I'm just going to jot these down. Iron 2 chloride versus iron 3 chloride. And we already know this. We already know that this transition metal has multiple oxidation states. You've heard me throw that term out. Well, in this video, I'm really going to kind of tease the differences between charge and oxidation state and oxidation numbers so that you can have a more holistic picture of these new redox reactions. We know that this iron here is a charged metal, and this one here, we know this. If we were to assign oxidation states, we would assign them as such. And at this point, you're probably thinking, okay, this is exactly the same thing. Well, we're going to go through several examples, and I'll expound on all of this here in a minute. First things first, I want you to go ahead and get out your rules for oxidation numbers. This was given out to you in class, and if you didn't receive them in class, it's available on pedersenscience.com. I'm going to go over these individual rules, and then we're going to do 5 practice examples. All right, so when a species is in its elemental form, its oxidation number, which is synonymous with oxidation state, it's a number that is being assigned, is 0, okay? Monatomic ions, you're going to match the ion's charge. And again, at this point, you're probably thinking, Mr. Pedersen, what's the difference between oxidation state, oxidation number, and charge? So I want you to take a moment and jot down this definition here. And then hopefully it'll make more sense after we work through several examples. So I'm using the word apparent net charge an atom would have. Okay, so apparent, that's very important. When we assign oxidation numbers, it's really just a bookkeeping task, all right? Not all of the species are actually charged. For example, if we look at carbon dioxide, that is a covalent bond, like they're sharing electrons, okay? It's not like an ionic compound where we look at donating and accepting electrons and then subsequently attracting to one another. And I would also like to say that there's a term here, electronegative atom, and we haven't explicitly covered that in class, and that's okay. All right. My idea is the more I can expose you to some of these terms, the less foreign they'll be later on in the course. So these are terms that I'll use when we start talking about atomic theory, periodicity, and bonding. But it's okay to use it now because we're going to come back and revisit all of this. So an atom would have this net charge, which is an apparent net charge. If the covalent bond belonged entirely to the species that had the greatest electron affinity, all right? And an oxidation number is simply the positive or negative number that corresponds to the oxidation state. All right, so let's continue going down this list. I feel a little bit better giving you some sort of definition there for you to at least consider as we go through these. For hydrogens, we're going to give them a +1 oxidation number with the exception of when they are part of a peroxide. Remember, a peroxide is one of your polyatomic ions given out to you that you should be familiar with. When we're looking at compounds that are not overall charged, the sum must equal 0, okay? The sum equals 0. We're going to go over some. However, when we're looking at oxidation states of polyatomic anions, or any polyatomic ion for that matter, the overall charge must match the charge of the ion. And then, of course, we're going to give the more electronegative element a negative oxidation number. Now, electronegative means the species that has the greatest affinity for electrons. All right, so at this time, we're going to go over some examples. Carbonic acid, H2CO3. Okay, this is carbonic acid. And so a lot of students say, well, where do I start? What I would do is start with hydrogens and oxygens. So, of course, hydrogens are +1 unless they're associated with a metal hydride over here. This is not the case. So we have each one of these being +1, and there's 2 of them. So that's going to equal a +2. Now, at this point, I want to mention one more thing, and it is minor, but it's important to me that you know. When we are assigning oxidation numbers, the charge comes before the number. When we're indicating charges of species, be it monatomic ions or polyatomic ion, the charge always comes after the number. And it might seem minor, and indeed it is, but it's important to me going forward that you understand there is actually a difference and there is actually a correct way to write these. All right, let's look at the oxygen here. Oxygen -2, and we have 3 of them, and so that'll give me a -6. So the question becomes, what is carbon? What is carbon? So 2 minus 6 plus blank equals 0. Okay, we want this to sum to 0. There is no net charge on this ternary compound. All right, so what's going to equal 0? Well, we have here -4 plus blank equals 0, and now it's pretty obvious, +4. So carbon's oxidation number in carbonic acid is +4. Next example, phosphate. This is a polyatomic ion. Notice how I've written it here with the charge after the number. And where do we start here? Well, first off, we acknowledge there is an overall charge. And when it's all said and done, the charges of the oxidation numbers should equal the charge of the polyatomic ion. We'll start with oxygen. 4 oxygen times -2 equals -8. So phosphorus equals, we don't know. So blank plus -8, however you want to write this is up to you, equals -3. Phosphorus in this case has an oxidation number of a +5 in the phosphate polyatomic ion. Okay, and you see this here, that this overall, when we sum this, we end up with -3. -3 matches the charge of phosphate at 3-. Next example, iron 2 nitrate. All right, so in this structure here, again, where do we start? Well, one thing you should know, and I would encourage you to try both ways, is use your knowledge of polyatomic ions, okay? You know nitrate, and you know that each nitrate is a -1. So you can use that to figure some things out. Okay, I'm going to go through and do this the long way. Okay, we'll start with oxygen. That's a great spot to start. So, so I have 3 oxygen per nitrate, but I have 2 nitrates. So I actually have -2 times 6, which gives me a -12 for oxygen. Again, let me show you where that came from. 3 times -2, that's where the -6 comes from. But then we have -6 times 2 because there's 2 nitrates, and so that's where this comes from. All right, now let's come back over here and look at iron. Well, we know this. We've learned this, so use it to your advantage. All right, iron has a +2 oxidation number. Okay, and now all we need to do is figure out how we can get this to equal 0. Okay, now we have a +2, we have a -12, and we have a blank, and we want to equal 0. All right, so we know that this would need to be a +10. Nitrogen's not +10, but there's 2 of them. Okay, so I'm going to go ahead and rewrite this because I just realized where I was writing. You probably can't see. Sorry about that. Okay, so I'm going to rewrite it and show you it right here. So we know that it's each nitrogen times 2 equals 10. Therefore, the single nitrogen oxidation number is going to be +5. All right, so a +5 is the oxidation number for each nitrogen. There's 2 of them. 2 times the +5 gives you the +10 that we need for this entire summation to equal 0. Sodium phosphate. All right, let's go ahead and knock this one out here. Again, I mean, we can go ahead and say 3 times +1 equals +3 because we know that sodium is a +1. There's 3 of them. We also know that we have 4 times -2, which equals -8 for oxygen. So we also acknowledge we need the sum to equal 0. There's no overall net charge. So +3 plus -8 plus blank equals 0. And hopefully it's clear that a +5 number for phosphorus would sum to 0 in this case. All right, last example here. I like to throw this one in here, hydrogen peroxide. All right, so we are dealing with a peroxide, so we need to be aware of that. 2 times -1 equals -2. And hydrogen, nothing funny going on here, so we can say that +1 times 2 equals 2, +2, excuse me. And so these sum to 0, therefore The oxidation number for hydrogen, this is pretty easy, was +1. And the oxidation number for oxygen, -1. Okay. So one thing that I want to mention is this is a pre-AP chemistry course, so we're going to have lots of forays into AP Chem territory. In this case here, we were working on one of the College Board's big ideas dealing with redox. There's a couple more podcasts in this series where you're going to continue looking at oxidation reduction reactions and learning a little bit more about them. And as you may have guessed, there is a problem set that is now available, and I want you to start working on that problem set and trying to put all this together. So thank you very much.